Right. Good afternoon, everyone. Today's topic is new synthetic reactions. So in that we have the different types of details are there. So we have 7 types of new synthetic reactions are available. So first one is metal mediated CC and CX coupling reactions, and CC double bond formation reactions, and multiple multi-component reactions, and Yugi ring formation reactions, and click chemistry, and metathesis reactions, and other important synthetic reactions. So today's topic is metal mediated CC and CX coupling reactions. So how many reactions are there for our study? So first one is Suzuki coupling reaction, and another one is Heck reaction, Still reaction, and Sonogi-Shira reaction coupling, that is another coupling reaction, and Buchwald-Hartwig coupling reactions, and Nigishi-Kumada coupling reactions. So today we will deal with Suzuki coupling reaction, right? So in this, the palladium catalyst is used, and this palladium catalyst cross coupling reactions was developed by the 3 people. That is, those are Richard F. Heck and Ichi Nigishi and Akira Suzuki. These people were awarded the 2010 Nobel Prize in Chemistry because of the development in by development of using palladium catalyst for cross coupling reactions, right? So the first one is Suzuki coupling reaction. So here palladium PD shows variable oxidation states like PD0, which exhibits 2, 3, 4. So this palladium is a d block element, and here the palladium, if it lost the 2 electrons as an oxidation reaction, then it will get the palladium +2 state, and if it gains the 2 electrons, then it gets to 0 state. And same thing, if it is having 2 electron +2 state, so if it loses 2 electrons more, then automatically it converts into palladium +4. And these are the some palladium catalysts are available. So the first one is tetrakis triphenyl phosphine palladium 0. Another one is bis triphenyl phosphine palladium 2 chloride. Another one is palladium acetate. The fourth one is dibenzylidene acetate, that is palladium. So here we can denote this palladium catalyst with LNPD. L is ligand, and N is number of ligands are available, and PD is palladium. So this is a basic example with RX. Any halogen contain alkyl halides, and R1 BX and boron substitutions are available. So if we use any palladium catalyst with solvent base, so we will get this coupling of R dash. So where here R dash are the alkyl groups or aryl groups or alkenyl groups or allyl groups, alkenyl groups, or we can go with heteroyl groups also. And here R1, we can use some triflates also, right? Mostly used solvents are ethers, benzene, and THF. And base is available for the reaction sodium bicarbonate or sodium hydroxide, potassium hydroxide, or CS2CO3 or KFR, NaOR, some etc. So what are the advantages and disadvantages of this Suzuki coupling reaction? So advantages are the starting material, that is organoborates or palladium complex, are very cheap and available in the market. And all compounds are non-toxic and it is easy to handle. Yield of the product is high, mostly 70 to 80% yield is available. Sometimes we'll get the 90% yield also. And another one is on a difficult carbon skeleton also we can create or we can establish a C-cis bond. And this C-cis single bond can be formed on a difficult skeleton positions also. And here another possibility of reaction is advantage of this one is we can go with the stereo and regio selective reactions. So it is also possible by using palladium catalyst. And disadvantages is, or the most disadvantages only one, that aryl halides are sluggish in Suzuki coupling reaction. And due to the presence of base, if chiral center is present, then racemization takes place. The another one disadvantage is ligands used in these reactions are often air sensitive or moisture sensitive. Post-reaction purification, which requires a column chromatography and recyclization compulsory. So we'll get we have to perform the recyclization and recrystallization. Sorry, recrystallization and chromatography we have to perform, right? And synthesis of boronic acids. So here we are using the boronic acid experiments. So here boronic derivatives are available. So for that we have to go with this boronic acids. So synthesis of boronic acid from Grignard reagent. Here aryl magnesium halide. So boron is available with the trimethoxy borane, and we will get aromatic boranes. And same thing alene, or we can go with alkyne substitutions. So this will be used in the reaction, right? And the next one is from organolithiums. So in organolithiums, alkyl lithiums are used with boron type. Boron lithiums or organolithiums are more reactive, and here we also get some molecules with products with this organoboranes, right? And aryl boronic acids from alkoxy diboranes. Here also we can see the benzene toluene molecules with substituted Y. So here we will get the methyl group is replaced with boronic acid groups. So these are also, we will use the boronic acid with substituted bromine, any alkyl metal groups. So transfer of this bromine means the transfer of organic group from one metal to another metal is called as the transmetallation positions. So this boronic acid position will be reacted with the bromine, and these two phenyl groups, the third reaction, these two phenyl groups will be reacted. And this is the catalytic cycle of Suzuki coupling. Okay, so here it is a palladium 0, and X is reacted with the palladium 0, and you will get a palladium with +2 charge, and aromatic group and halogen has been incorporated in this as a product. And this one also we can see, right, this one. And here you got the palladium 2 position. And by using the sodium hydroxide, the elimination of sodium halide will be there. The two halogens are bromine or iodine. So here you will get the substitution of OH in the place of halogen. Same as it is here also we can use these boronic acids, aromatic boronic acids. So these three boronic acid OH groups will be available, and this aromatic ring, so another aromatic position will be attached to palladium catalyst. So like this you will get the reaction with two moieties of organomoieties, two organic moieties attached to a single bond. So this is the catalytic cycle for Suzuki coupling. So how the palladium metal or metal mediated reaction has been taking place. All right. The next. Right, this is another example. So these are the some examples which we have selected here. Okay. Okay. So these are the some reactions which are available here. So we will see those also. So this was erased. Okay. So this is a phenyl bromide with alkyne substitution. This is a phenyl with alkene substitution bromide, and this is a boronic acid. And here you can see This is the borane. This bromine was eliminated. This bromine was removed by this boronic ester. So this part has been removed, right? So now you can see this double bond and this double bond is available. These two double bonds are available, right? So this was prepared. So here the new bond formation will be done. This one means bromine was eliminated, and here bromine was eliminated. So in between this double bonded position and this double bonded position, the bond has been generated. So two groups, the double bond groups are established. So in between there is a C-C single bond generation was done. The same thing OTF, these are the triflates. So in this triflates also, so here you can see the chlorine and this boron moiety. So the new carbon bond was established in this two ring system. So this is the ring systems bond, right? So this is coupling reactions. Okay, right? So these are the triflates. Next, Heck reaction. So this Heck reaction is another reaction, coupling reaction. So in this Heck reaction, alkyl halides and olefins are reacted. So in presence of palladium catalyst. So automatically this olefins, the C-C single bond, halogen elimination will be taken place, and substituted olefins were developed. So here you can use the R and R dash means alkyl groups as alkyls, aryls, alkenyls, alkenyls, as well as allyls or benzyles. So the C-C bond formation between alkyl halide and olefin takes place in the presence of a base is known as Heck reaction. If any electron withdrawing group is present in the starting material, olefin leads to decrease the rate of reaction. If any functional group such as OH or NH2 or COH group, carboxylic or amine group or alcohol groups will not influence the rate of the reaction. So in general, the palladium 2 catalysts are used in this reaction. So this is the palladium catalyst cycle. So here you can see the conditions, right? So here palladium 2, right? So this is a palladium 2, and here alkyl halide has been used. So oxidative addition reaction. So in oxidative addition reaction, one side alkyl, another side is halogen groups are substituted on the ligand palladium group positions. So automatically here you can see the one ligand will be eliminated. So here two ligands are there, but here only one ligand is available. So ligand elimination was taken place. So automatically the substitution, the alkyl group which is there, which is involved, and here double bond. So this double bond was interacted with the metal palladium. So this is called as insertion of metal palladium, that is a ligand. After insertion, the double bond was converted into the second single bond. So this bond has been formed. So here R, C, so C, R. So palladium catalyst will be separated out from this, and here you will get the alkyl group formed, the C double bond C formation, right? And so automatically ligand with, and again it was beta hydride elimination method. This is called as a beta hydride elimination method. So automatically here you can see, so these two are the same because here two ligands are available, here also available, but here one ligand was reduced, again here the ligand was incorporated, and by using the base the hydrogen halides will be eliminated. All right, so this is the another reaction. So this is the life cycle or catalytic cycle of the reaction. Okay, and here palladium will be added to the highly substituted olefinic carbon, and the organic moiety to the less substituted carbon. So aryl halides are sluggish in head reaction. Isomerization of double bond takes place. Okay, tetra substituted olefin preparation is a difficult position because here it is difficult because it is a trans substituted one. So whatever the position of double bond is here available in the product, you will get a trans substituted. So if it is a trans substituted, there is only one substitution is possible. If you want to go with a tetra substituted means it is a very difficult because the palladium catalyst will be is a selective condition. So palladium will be attacked towards to the less that is double bond towards to the highly substituted one, and less substituted side position will be attacked towards to the alkyl group, right? And some of the examples are here available. So here you can see, right? So this halogen is removing, and here you can see the substitution will takes place at this particular position. Okay, yeah, you can see. So this was substituted here at this position. So automatically you will get at the double bond position CH3 another CH3, right? And here also you can see the iodine was removed here, not the bromine. Iodine was removed and substitution was taken place at this particular position. So here also you can see the bromine and this ethyl group. So here also you will get a bond formation in between these two. Here also in between these two bond formation. Here also the bond formation in between these two. So this is the best method for preparation of di-substituted olefins, right? So that's all for today. So tomorrow we will see another 2 or 3 reactions of this type, right?